Okay, so in this tutorial, I'm going to teach you how to run the 2D simulation code developed in our lab. So the structure we are going to study is a very common LED structure. We have P, N, and the contact, one is on top, one is on side, and this is a structure. This structure is similar to the 1D structure. The difference is that this is a 2D, so the current is not flowing from bottom to top, but it's flowing from the sideward. Okay, so in the 2D program, when you click this 2D program, the first interface you can see is this. So in the beginning, we say project, we say PN dial. Okay, we can save as a project first. So we say the desktop, okay, we say project 2D. Tutorial. Okay, so this is project 2D tutorial, and sorry, I think I should say project 2D tutorial a folder. I should create a folder. That will be better because you will generate a lot of files. So it's better that all the data is saved in the folder. So we go into this folder and we save file in this folder. Okay. So this is the interface. So in the 2D, we separate into three major regions. One is like in the 2D class, we need to set up the material region, and then we need to set up material parameter, and we need to set up the mesh. And the method used in this tutorial class is using the finite element, not finite difference. So the better part for finite element is that its flexibility to assign a boundary. But if you want to use this to calculate, use this finite element to calculate certain conditions, sometimes it's not convenient. But finite element has advantages that the boundary is always typically something similar to the Newman boundary. Okay, so you don't need to assign too much for those L surface. But sometimes I must say we should still be careful. So the first interface, as you can see, is still like 1D. You need to set up a layer, and usually we say bottom grown to top. So we can set up a layer. So the first, this is the case we are going to model. So the total width is 130 nanometer. So I should say the width is 130 nanometer. Okay, so I can generate, and I can start to add layer. So I can add one layer, and the first layer we can say is 3 nanometer. Okay, as you can see, this is we can say this is a 3 micrometer layer, but you can also say it's a 4. Okay, so if we want to say this is a 4 micrometer layer, then we can put this is 4 micrometer, and materials is InGaN, and the composition is GaN nitride, and it's N-type. The doping is 5E18. So we can apply. So this is the first layer. Okay, you can find this. Okay, so this is the first layer, and then we can add a second layer. Second layer, we can say it's a quantum well, quantum barrier, quantum well, quantum barrier. So by the same way like 1D, we can add one layer, and if we say this is a quantum barrier, and we can say it's a 10 nanometer. So it's 0.01. The unit is micrometer, and it's indium gallium nitride, and the composition 5E18 doping. So I can add another one. It's very thin, you can see here. And then we can put additional layer 0.03, 3 angstrom layer, 3 nanometer layer. And the composition here is 0. Okay, it's a quantum well, so we say it's 0.17. The composition Y, and it's intrinsic, so it's 1E17. Okay, so if you look at this layer in this structure, and then you can magnify this structure, you can find we put 1 or 2 layers here. So we can add more. Okay, so very similar to the one, and if you are lazy, so we can put, this is a barrier well, so we have another 5 barrier and a well. So we totally need to add 10 layers. Okay, so I can say I'm going to add 10 layers, number 10 layers, and thickness is 0.1. We can change it later. And then the composition is 0 and N-type 1E18. So actually it's 9 quantum well, barrier well, barrier well, barrier well, barrier well. So it's okay, it's 10. Okay, that's right. So we can put additional 10 layers, and if you look at here, it's here. So we can modify. We can modify because for this layer, okay, you can find this, okay, and this. These are quantum well, so the thickness is 0.03. Okay, we can apply. Okay, so right now the thickness is changed to final 6 quantum well. And if you look at this, you can see this is a barrier well, so there are 6 quantum well. Then finally, we can put the P quantum barrier, P-type aluminum gallium nitride, and the P-type gallium nitride. Okay, so we can add additional 3 layers. So the first layer is 10 nanometer, and the composition is 0, and it's P-type, and it's 5E18. Okay, we can say it's 5. Let me see. Okay, it's P-type 2E19. So we can say 2E19, and we can apply 1 layer, and then I put additional layer is 30 nanometer, so at 0.03, and the composition is aluminum gallium nitride, so it's 0.1. Sorry, so is that there? Okay, no, I didn't add successfully. So it's aluminum gallium nitride layer, and thickness is 0.03, and it's P-type, okay, and the composition is 0.1. Apply. Okay, so the final layer is 0.15 micrometer, and it's indium gallium nitride, composition is 0, composition Y, and it's P-type. So finally, you can find this is the well structure. Okay. So this is barrier well, and the barrier, and the EBL, and the gallium nitride. So this is the final structure. Okay. But after this, we can do the modification here. Is just the structure layer thickness. So, but remember, in this part, okay, we have different settings. For example, material parameters. Okay, if we go into the right-hand side, we already generate the material because we already choose the material. But the problem is the quantum well. So in here, I can manually modify this. So you can find the parameter is changed. Okay, but actually this is not assigned yet. So we need to generate the default parameters first. So after generate, you can find all the material parameters is generated. And if you look at here, okay, you can find there's a problem is that this is indium gallium nitride, but this is gallium nitride. So it's not right. Okay, even if you refresh it, okay, this is a new data. There are two indium gallium nitride layers. But if you're going back to the original structure, then we should have a six quantum well. So I can either do this or I can modify here. So I can say this 2 is already indium gallium nitride, so I can choose the rest 4 layers. Okay, I can change the composition of indium gallium nitride to 0.17, and I can apply. And as you can see, okay, we refresh. Okay, it's not successful. Sorry, I should choose this 4. I didn't choose. Okay, composition 0.17 and applied. Okay, right now it's applied, and okay, you can find it for 6 quantum well. So all the AP layer is designed and finished. Okay, so this is the AP layer. Then, okay, you can change the width from here. So the set layer region is that actually we have this part. There's no material here, so we need to try to amplify. So not amplify, and try to make this erase this part. So I can use the empty function. So it's very similar to the first version. We can put 1 layer, okay, and it tells us that what kind of material region you want to remove. So I say it's a rectangular, and I need to move away this part. So I say the F1, okay, its lower part is in 100 micrometer, and F2 is 3.0, and F3 is right hand side, so it's 130, and then on the top, okay, on the top we need to check what's the top. Okay, maybe 4.3. Okay, we can put more. Okay, apply. So I have this section to be removed. So this is a layer. Then I can put contact. Okay, so after we set up the mesh, okay, mesh setting, then we can go back to this contact. So we can say that, okay, there's a linear contact, so we should put the first contact, okay, we want contact region to be from 0 to 80. So we can say, I want to add a contact, and then this contact is from 0 to 80, and we can say it's a joint contact on the top. So after that, you can find there's a contact here, and this is a source contact. So I can add another source contact, and this is from 110 to 130, and this is source on the top. So no matter if source or top, if this is empty section, this contact will drop down to this area. Okay, so I can set up the contact here. Then this contact actually is ready for start to do the simulation. Then finally is the mesh. So I can use the Coarse Mesh method mesh. So you can find that it will define the mesh for you. And we can make a real mesh. So we can finish the mesh setting. And if I plot the mesh, you can find the mesh is very close, but it still will do a fine mesh in the quantum well region. So of course you can choose the fine mesh, and then you can make the mesh again. Sorry, too fast. I need to make generate first, and then make mesh again. And you can find after you finish, refresh, and then plot the mesh. Then after that, you can find that the mesh become more dense, and in the quantum well, you can see in the y direction it's separated into more points. Okay, so for demonstration, I just use the Coarse Mesh, and then because I want to make it faster, so I make a Coarse Mesh, and I make it again. Okay, and refresh, plot. Then this is the mesh. The program will do automatic mesh, but of course you can manually change the mesh. So if you want it to be more dense, you can manually change the mesh on here. Okay, change the position of the node from 0 to 80, 80 to 100. Or you can change the ratio required minimum ds, dy. The program will calculate for you. But if not, just choose the Coarse Mesh and remesh. Then this is finished. So after the setting, so I need to save as okay. I want to save on the desktop, and I add new project called project 2D. Okay, tutorial. Okay, originally I save on a desk. It's not good. I save in the folder. Then I can save it. Project 2D DD 2D tutorial. Okay, so I can save the project, and then if everything is right, let's check the mesh, the material, the doping, and if everything is right, I can run the program. Okay, I can run the singlet simulation. Yes, and then we can start from VD equal to 3 or maybe to 4.0, and the VD step I can say is 0.1. Okay, it's a large step. And if you have get contact, you can set up Schottky barrier. And if you have drain and source contact, it will be the OMI contact. But you can put additional barrier if you want. Okay, if you have base reference, there is also additional contact barrier. And this is a resolution. This is maximum iterative. If it's not converted, after 100 steps, it will stop. This is the temperature. So save it, and we can run. Okay, so if you check everything's right, you can see VD start from 3 to 4, and they start to solve. And it's step 1, step 2, start to iterative solve the program. So you can see it start to get converged. Okay, it will take some time because this is 2D simulation. So we can take a break here. After taking a break, we can find the program is still running, but we can find for the VD equal to 3, okay, it's get converged. And the 3.1 is also get converged, and it's running to 3.2. So we can keep the program still running, but we can look at the result. So if we look at the result, we can check the BIOS dependence. So this is 3 volts, and okay, we have 3 volts, so we can plot it the conduction band potential. So for this conduction band potential, okay, we can find that this is a band profile, and if you take a look here, okay, You can see this is the quantum well position. Okay, there is a piezoelectric polarization. Okay, it's not easy to understand the plot, so we can plot at the 60 micrometer E minus 4 centimeter, and we can plot in the X direction, and you can see this is the conduction band profile. Okay, this is a quantum well, this is a band bending. Okay, so we can change it to different voltage. Okay, if I press 3.1, I can see it here, and this is a PN junction is here. Okay, I can use the hold down command, and I can plot EV, and then, okay, you didn't see that, that's fine. I can change the scale. So Y minima is minus 3.8. Okay, I apply here. Alright, I can see this is a valence band, and I can also plot the whole Fermi level, and this is the electron Fermi level. So you can find that maybe the holes only reaching the first quantum well, and the first quantum well electron is not reaching. So the recombination may not be very strong here. Okay, so you can refresh the data again. Just remember every time, because the program is still continue to run. Okay, you can find the program still continue to run, and then if you look at this, it's 3.7 volts. So if I come back and refresh it, I can also plot the IV curve. Okay, so IV curve, we can say I want to plot the source current and the gate voltage X, and we can plot it. Okay, this is the IV curve, and you can see this is 2D simulation, so the unit is m per cm square per cm, and we can normalize this, and we know the chip size is 130 micrometer. Okay, maybe you can say it's 0.01 centimeter. Okay, because the chip area here, okay, if we define this area, this is the current flow area, and it's 100 micrometer, and we can plot again, and we can see the current density here normalized is become m per cm minus 2 m per cm square. The current density is still very low, and this is because the piezoelectric polarization will block the current. So we cannot see very good current, and but anyway, we can look at the many different data. We can see the conduction band. We can find the radiative rate. Okay, at 3.7. You can plot the radiative recombination. It will take a few times, and you can find this is a radiative recombination. You can almost cannot see anything, but you can magnify larger. This is a quantum well, and this is, you can find the light is emit in the first top quantum well. So again, let's say the last quantum well. People say growing from this to this, so this is 6 last quantum well. So this is the tutorial to run the 2D. So you can see a lot of different data. Or if you want to see the element base, you can plot the electric field and the current flow. Okay, this could be an electron flow or current plot. Okay, and if you plot Jn, okay, you can plot the current density as a absolute value of current density, and you can see there is a current here, and okay, this is for heat plot, so there's no heat data, so you cannot see anything yet. And of course, you can check a lot of different results like ray tracing, triangular mesh, these kind of things later. But since they are not there, so if you plot it, you cannot see anything. Okay. And node base, node database, you can plot this EC electron hole, dopant impurity, trap, generation rate, radiative, non-radiative object temperature, and if you use localization landscape theory, you can get something like this.